So rate of crystallization is very important factor that determines how perfect or imperfect the crystal will be grown. Okay, these imperfections can be of various types. For example, there are three types I have enlisted here. One is called as point defect, another is called as line defect, and let me tell you this, there exists something called as plane defect also. Tell you, even in your syllabus the detail is only about point defect, not even of line defect. But since they have mentioned that there are various levels of defect possible, what is point defect? This is like an irregularity in the arrangement of lattice point, individual lattice point. For example, I am just giving you the diagram here. You can see that if you have very systematic arrangement of lattice points extended in 3 dimension everywhere, okay, in 3 dimension, this direction, okay, across this direction or across z direction, anywhere if you go, you will have very nice lattice arrangement, systematic lattice arrangement of lattice points. But somewhere if you observe one or two location, you will find that either the particle is missing, or in some cases there are extra particles like this somewhere in the voids. The voids are bigger enough for them to occupy some extra points also. So, but they will not be in very big quantity. Let me tell you, when I am talking about this imperfection, this is still a crystal, but in the crystal the nature of element or ion, and also the nature of voids, that allows either the missing of some of the particle from their regular sites, or some of the extra points may be found in some of the voids also. So these will lead to imperfections. But if you happen to encounter them in the form of, let's say, individual lattice points like one, then you don't have anything here and there in any of the direction, then somewhere you may find one more, then these are all called as point defects. So point defects are simply irregularities associated with the arrangement of individual lattice points in the solid. Individual lattice point is the important term. In the similar manner, if you find this kind of defect extending in the whole of the arrangement of the particle, although that diagram I don't have here, and anyway it is not discussed here, but you don't have the imperfection. For example, I just tell you, if you observe the crystalline solid, everywhere you may have the lattice point, but let's say only one row of the particle is missing, only one row of the particle is missing, let's say. For example, in the systematic arrangement of that sodium chloride or any of them, only one particular row, one line is missing, okay, then that missing, or there could be extra also, okay, then that kind of imperfection is called as line defect. Irregularity associated with the arrangement of entire row of the lattice point. This is one dimensional defect. This is zero dimensional defect. Point defect is a zero dimensional defect. This is one dimensional defect. And suppose if you extend the defect in 2 dimension, like one whole plane of the lattice point is either missing or extra plane is added somewhere in the void, that will also lead to irregularity, that is called plane defect. Anyway, this is not discussed in your syllabus, so don't worry about that. But line defect, you understand, point defect simply means one or two, it is more of a location defect, okay, one location versus another location. Okay, so we will go further in the further discussion, elaboration on point defect only. Your syllabus only emphasizes on looking at various kind of types of point defect, so these are not there to be discussed further. Okay, point defects, again you will keep finding the subdivisions in each of these. Point defect have 3 types, major 3 types. One is called stoichiometric defect, another is called non-stoichiometric, and another is called as impurity defect. These 2 defects are like, more of within the substance by its constituent particle itself. ओके, मतलब इसमें क्या होता है, जो सब्सटेंस है उसके अलावा कोई फॉरेन एलिमेंट प्रेजेंट नहीं होगा. जो जैसे सोडियम क्लोराइड का अगर क्रिस्टल आप एग्जामिन कर रहे हो, तो उसमें जो डिफेक्ट है उसमें केवल सोडियम और क्लोराइड आयन के द्वारा ही डिफेक्ट होंगे, चाहे वो एक्स्ट्रा हो या कम हो. बट इम्प्यूरिटी डिफेक्ट्स में क्या होता है, कुछ फॉरेन एलिमेंट जब आप ऐड करते हो या किसी तरह से ऐड हो जाते हैं किसी क्रिस्टल में, तो जो डिफेक्ट आते हैं वो इम्प्यूरिटी डिफेक्ट कहलाते हैं. वी विल गो वन आफ्टर द अनदर स्लोली. ओके, so talking about the first one, which is stoichiometry, as the name suggests, please see, as the name suggests, stoichiometric defect will not disturb the stoichiometry of the substance, but in non-stoichiometric defect you will have stoichiometric being disturbed. For example, just to tell you, just to get you into the rhythm here, For example, if you talk about the NaCl crystal, okay, the defect of NaCl crystal will have both Na and Cl anywhere being observed. Overall the ratio will be 1 to 1. Overall there may be defect, but those defect will be balanced by counter ion also, counter ion defect also, okay, but always in the whole crystal NaCl will be found in 1 to 1 proportion. In non-stoichiometric defect, for example, best example is iron oxide. If you examine the crystal of iron oxide, most of the places you may be finding 1 to 1 only, but some region you may find FeO in the ratio of 0.95 to 1, what is supposed to be in 1 to 1, but it's not. So why is this? We will see that, okay. And as I said, impurity defects will be because of the foreign element. So let's first start with the first one, which is stoichiometric defect. Although I have taken the example to talk about this as an ionic crystal, but you should first discuss this with the simple lattice system where the substance may not be ionic also. For example, metals are more like, metal solids are more like atomic arrangement, particles atomic arrangement. But if you talk about the molecular solid, they also have individual lattice which are of only one type. Ultimately I am saying that we are talking here the atomic or molecular solid means only one type of lattice points, and here in ionic solid you have more than one type of lattice points. Remember, we are talking about stoichiometric defect, but stoichiometric defect now in different type of crystal will be discussed differently, okay. We are taking two different type of crystals, one is atomic type and stoichiometric defect in ionic solid. Defect, the fundamental point to remember is that in the whole of the crystal overall the stoichiometry of the substance will still be maintained, it will not vary, unlike non-stoichiometric defect like this. If you talk about atomic or molecular solid where you have only one type of lattice points, then you have a different story to be discussed, and little bit different story when you talk about ionic solids where you have more than one type of lattice points. Is it clear? Now we will go further in this. As I said that we are talking about only one type of lattice point. What happens? There are two type of them. One is called vacancy defect and another is called interstitial defect. What are they? Let's see. One is called point defect, one type of point defect in case of atomic or molecular solids of vacancy defect. These type of defects arise when once in a while you encounter the lattice site empty. That means you don't have lattice point there. There is a vacancy. And not that I am saying ki after every alternate lattice point you will find that. No. The number will be very, very tiny. 1 in million. It's like that. 1 in 1 million could be of that order. Okay. 1 in 2 million or many, many millions. But still these defects matter a lot. So I am saying that these kind of defects where you have missing of lattice point. Lattice point is missing. Lattice point or lattice motif is missing. Okay, very few, okay, few of them are missing. So that kind of defect is called as vacancy defect. Do you agree that if you don't have all the lattice points being occupied by the atoms or molecule, that will affect the density? Do you agree with this? Somewhere it will lead to, it may be very minimal difference, but it will definitely affect the density. So this kind of defects lead to certain decrease in density. I am not saying the density का decrease बहुत ज़्यादा होगा, बहुत ही टाइनी होगा, बट इट विल डेफिनेटली डिक्रीज द डेंसिटी फ्रॉम व्हाट यू एक्सपेक्ट फ्रॉम अ रेगुलर अरेंजमेंट ऑफ द पार्टिकल. ओके, so this is one thing. In contrary to this defect, in the similar type of lattice where you have only one type of lattice arrangement, sometimes you find extra lattice points, extra lattice motifs. There are example of this kind of lattice also. So there is no vacancy but extra arrangement. Okay, so these kind of lattice motif, these are extra lattice motifs. They will certainly increase the overall density of the solid. Okay, when I say density means I am talking about average density, overall density of the solid. So these two things you have to know. First of all, there is not much of further, we have to go further detail about how many of them there. If you look at any other book also, you will find that there are specifically the number on an average how many defects are there per unit volume and all those things, but we will not go into that except in one case, one or two cases where it has been mentioned. Otherwise we will not go into too much of detail, because idea is only to introduce ourselves the type of possibilities that the defect can happen and in a perfect solid also. Okay, so I just said in stoichiometric defect we just talked about, based on if it is a single type of lattice, then you can have a defect which is called as vacancy defect, and this kind of defect is called as interstitial defect. Why it is called interstitial? Because it has acquired some of the extra points have acquired the interstitial sites. These sites are referred, the voids that we generally talk about, these are called as interstitial sites, extra lattice points or lattice motif in interstitial sites. Again, as I said, these are not going to be in a very big number, 1 in million or something like that. Okay, here diagram shows 2 very close, but need not be very close, they may be very far away. Okay, fine, and definitely this will decrease the density. Well, the story is a little different when we talk about ionic solids. Why? Because any species which is ionic, it will maintain the charge neutrality, correct? And when charge neutrality is important, then you don't expect ki only one type of ion missing and another is still left out. Somewhere the balance of charge has to happen. I am talking about balance of charge is necessary. So if one kind of, for example, in this kind of example, I see that suppose in this crystal of sodium chloride, where sodium are like, you know, the blue circles or spheres, the tinier one, and bigger one are chloride, negative ion. In this region the chloride ion seems to be missing in this region. Okay, this should have been chloride ion here. So there is one kind of missing element ion here. But then, as I said, because the ionic solids have compulsion of maintaining the charge neutrality, ionic solid must maintain charge neutrality. That requirement will make sure that there is counter ion also missing. In case if one is missing, the another will also miss. So this is more similar to vacancy defect in this kind of solid where you have only one type of lattice. Okay, but because this is an ionic solid, we have put it in with a different name. We call it as Schottky defect. Just a name, that's all. Don't worry about the meaning of that, but it's called Schottky defect. Schottky defect means you are imagining an ionic solid and where the vacancy is created because of missing of one cation and one counter anion in ratio of each other. There could be many cation, many anions missing, but they will always be missing in 1:1 proportion. Okay, so this type of vacancy this is very similar to vacancy defect in this case. Okay, it is similar to vacancy defect in case of the molecular solid. Okay, this will also lead to decrease in the density little bit, not much, and your book gives you some number. As I said, I don't want to give too much importance to this number, but let's say how many of these defects are generally found. As I said, if you take 1 centimeter cube crystal, which is a very big crystal, have so many, unlimited number of ions and unlimited number of cation, you get only 10 to power of 6 Schottky defects, very tiny number. Okay, don't think 1 million means 1 million per centimeter cube is a very tiny number, because in one cubical centimeter, approximately, your book I think probably gives you some number, the total number of ion pair are approximately 10 to power of, let's say, 28 ion pair. So these many ion pairs are very tiny in comparison to this, what I am saying. Okay, generally these kind of defects are found in the crystal where anionic and cationic sizes, the difference is very small, although there is always a difference. Cation and anions are generally very different, and anion is generally bigger than cation, we know this. But suppose if the difference is not too big in the periodic table, like if I compare NaCl versus NaI, tell me where the difference of cationic and ionic difference is more. If I compare NaI with NaCl, where do you think is the cationic and ionic difference large? Anybody? The cationic and ionic difference is higher here compared to this one. So I am talking about the relatively. Relatively, if the difference is not too big, then this kind of defect can happen. Because क्या होता है कि दोनों को ही निकलना है, दोनों का ही निकलना आसान होना चाहिए. तो वो कब होगा? तभी संभव होगा जब दोनों का थोड़ा सिमिलैरिटी होगा, है ना. तो ये शॉटकी डिफेक्ट जो है जनरली इस तरह के आयनिक क्रिस्टल में पाए जाते हैं जहाँ पे कैटायनिक एनायनिक डिफरेंस बहुत ज़्यादा नहीं होता है. ठीक है, ये एक चीज़ हो गई. उसी तरह का एक और डिफेक्ट है आयनिक सॉलिड के अंदर ही, जिसको हम दूसरा नाम देते हैं, जिसको कहते हैं फ्रेंकल डिफेक्ट. नाउ फ्रेंकल डिफेक्ट जस्ट कॉन्ट्रारी टू दिस, इट इज जनरली फाउंड इन द सॉलिड्स वेयर द एनायनिक कैटायनिक डिफरेंस इज लार्ज. ओके, जहाँ पे कैटायन जो है वो एनायन से सच में ज़्यादा छोटा है. फॉर एग्जाम्पल दीज आर सम ऑफ दोज क्रिस्टल्स. ओके, सो व्हाट हैपन्स इन दीज काइंड ऑफ डिफेक्ट्स? ओके, इन दीज काइंड ऑफ डिफेक्ट द कैटायन and anion are not missing completely from the solid. Like in this case, you saw that there is a completely missing anion, completely missing cation, and they are out of this solid. But in this kind of case where you have, let's say, cation to be of much smaller size than anion, then this guy which is very tiny, this void, okay, who decides the size of the void? The size of the void will always be decided by the bigger candidate, right? बिकॉज उनका पैकिंग जो है कितना बड़ा वॉइड यहाँ पे लेके आएगा वो उनके टच पे डिपेंड करेगा. तो अब छोटे से आयन को अगर उसमें रहना है तो वो रह सकता है बिकॉज इलेक्ट्रोस्टैटिक इंटरेक्शन आर देयर, बट देयर इज ऑलवेज अ पॉसिबिलिटी दैट दिस वॉइड बीइंग बिगर द कैटायन मे बी लिटिल बिट लूज एंड दैट कैटायन कैन समटाइम बी फाउंड इन सम अदर लोकेशन, in some other different kind of site, not at the same point. Of course, as I said that when we say defects, they are not very big in number, 1 in million, 1 in trillion kind of thing. So I am saying that, but they can still be happening. So the mechanism with which they happen is different compared to here and here, and it purely depends upon the size difference between the cation and anion. So यहाँ पे अगर आप देखेंगे कि कुछ भी मिसिंग नहीं है, केवल कैटायन जो है जो छोटा होता है कहीं से अपनी लोकेशन से मिसिंग है, जैसे यहाँ पे से मिस है, एंड देन इट हैज़ ऑक्यूपाइड सम अदर इंटरस्टिशियल साइट. ओके, सो दिस इज लाइक अ कॉम्बिनेशन ऑफ वैकेंसी, बिकॉज ओरिजिनली जहाँ से ये गया है वहाँ पे तो वैकेंसी क्रिएट कर दी, लेकिन कहीं दूसरी साइड पे गया है तो वहाँ पे उसने इंटरस्टिशियल साइट को ऑक्यूपाई कर लिया. तो दिस इज लाइक अ मोर ऑफ अ बोथ कॉम्बिनेशन ऑफ वैकेंसी एंड इंटरस्टिशियल डिफेक्ट दैट वी हैव सीन इन दिस काइंड ऑफ सॉलिड. ओके, वैकेंसी भी हो रही है और इंटरस्टिशियल अरेंजमेंट भी हो रही है. अच्छा, इस तरह के क्रिस्टल में डेंसिटी को अफेक्ट नहीं पड़ेगा बिकॉज ओवरऑल कुछ भी मास यहाँ से मिसिंग नहीं है, वॉल्यूम भी मेंटेन है ना, तो इसकी डेंसिटी उतनी की ऑलमोस्ट उतनी ही रहेगी. ठीक है, ये क्लियर हो गया. और इसको कई बार अलग नाम भी देते हैं, इसको कहते हैं डिसलोकेशन डिफेक्ट, simply because this is simply dislocated from its original site. Sometimes these defects, Frenkel defects, are also branded as dislocation defect. Non-stoichiometric defects. Non-stoichiometric defects are definitely, as the name indicates, Due to these defects, you are bound to have some non-stoichiometry in the formula being created for a substance. Appreciate. So, non-stoichiometric defect, I will first tell you how they arise, then we will go into the discussion of this discussion further. For example, let me take sodium chloride crystal. Okay, sodium chloride crystal, if you take, okay, a very tiny crystal it could be, or let's say the substance which is crystalline sodium chloride, and now I'm starting with an experiment, but idea is not to describe the experiment to create that kind of vacancy. Those kind of vacancy do exist. Okay, so suppose if we heat this with, let's say, sodium metal, okay, solid, or vapor of that, if it is exposed to this sodium particle, when you heat, they will be deposited on the surface of the sodium chloride. But then what happens once you have this sodium atoms on the surface of sodium chloride, on the surface itself, or from the layer beneath the surface, the chloride can interact with this sodium ion, and then now you know that sodium is a metal, it's a neutral atom. So chloride, how will that interact? Well, it will not interact initially, but this is a reactive atom. Okay, when the chloride comes in the vicinity, it tends to form a sodium ion, so that it can acquire a more stable state in formation of sodium ion and then form sodium chloride. So what happens is, in the crystal, from inside, just imagine, let's say some chloride has gone to interact with this sodium atom, and in the process this sodium has, let's say, in the interaction of chloride, it has created sodium chloride pair, ion pair, and इलेक्ट्रॉन इज लॉस्ट. ठीक है, तो अब ये हुआ क्यों है ऐसा? क्योंकि सोडियम कहीं से एक्स्ट्रा हमें सपोज मिल रहा है. दिस इज जस्ट द एक्सपेरिमेंटल सिनारियो आई एम सेइंग. When this kind of formation happens, now no problem here, sodium chloride is happy. But what about this extra electron? It will not remain on the surface, it will try to occupy more stable site, and definitely it will try to go to the region where vacancy is created by chloride ion. Chloride migrated from some location to interact with sodium atom, and then the electron created by this sodium metal now migrates to the location where chloride was originally. So anion की जो original site थी, वहाँ पे ये electron पाया जाएगा. Okay, now in the entire process, please see what has happened. Your entire sodium chloride crystal has ended up acquiring extra sodium ion, let's say extra sodium particle in the form of ion, of course, but there is excess of sodium in this experiment, है ना. आप एक्स्ट्रा सोडियम एटम अगर कंसीडर करें, खाली एक ही की बात कर रहे हैं हम डिस्कशन के लिए, तो इट इज़ एक्सिस एंड चार्ज इज स्टिल मेंटेन. देयर इज नो डिफरेंस इन चार्ज, बिकॉज आपने क्लोराइड को यहाँ पे जोड़ा तो उसके क्लोराइड के बदले इलेक्ट्रॉन भेज दिया, तो ये ओवरऑल जो चार्ज है वो तो वैसा ही है पूरे क्रिस्टल के ऊपर. अब होता क्या है, अच्छा, ऐसे डिफेक्ट को हम नाम दे रहे हैं मेटल एक्सिस डिफेक्ट. नाम यू शुड नो दिस. नॉन स्टोइकियोमेट्रिक डिफेक्ट्स आर ऑल्सो ऑफ टू टाइप. वन इज मेटल डेफिशिएंसी एंड मेटल एक्सिस. This defect that I have just talked about is a metal axis defect. So sodium is an axis, that's why, compared to the counter chloride ion. Electron in an isolated form generally leads to weird phenomena, strange phenomena, because it is a highly excited species. Let me tell you, electron apart, it is detached from, let's say, sodium. It is not supposed to be in space free. Of course it will be interacting with sodium ions, no doubt, but I am saying that it is still much freer than the valence electron in these ions. Now this specific electron can absorb energy in the visible region, and it does that continuously. It gets excited because it is very free, and it gets excited by absorbing the visible light, and it keeps emitting the light also. So generally it gives the color to the crystal. So generally you know that in sodium chloride crystal, sometime you may have seen this yellowish hue. Not always your sodium chloride crystal which is grown nicely will be perfectly transparent, but it will lead to some kind of color like this. So this color arises mainly because of electronic transitions by this electron absorbing and releasing the energy. Okay, so metal axis non-stoichiometric defect lead to these kind of arrangement. These kind of arrangements are specifically referred to as F center. The formation of F center, where the interstitial negative ion site is generally occupied by free electron, that is called as F center. And these F centers are responsible to give some kind of color to the crystal. The transparent crystal should have no color, but we get sometime color. For example, sodium chloride lead to yellow. Okay, sodium chloride lead to yellow color sometime. In the similar manner, if you observe the color of potassium chloride crystal, that is generally little bit a violet in color. Little bit, not much. Similarly, lithium chloride, if you observe, it seems pinkish. Pinkish hue, violet hue, yellow hue. So these kind of colors are generally observed in the crystal, mainly because of the formation of these kind of defects, which are called as non-stoichiometric defect, and they arise because of axis of the metal that is possible with the crystal for some reason. Not only because of this experiment that I have told just to explain, but those extra atoms or ions of sodium might be present while the crystal is being formed from certain process. Okay, so but you may have axis of electron, no, not axis, but this electron occupying some void in the crystal, and they are called as F centers, and they are responsible for the color of the crystal. Okay, just to complete with one more example in the metal axis defect itself, the zinc we'll discuss tomorrow only. But zinc oxide case, suppose you have taken the crystal of zinc oxide. Zinc oxide is a white powder, you know that. Okay, white. When you heat this, what happens is this will decompose, and decompose in a manner that you get zinc 2 plus ion and oxygen being released. So oxygen gets out of the sites and extra zinc is left, but to maintain the charge neutrality, because this is nothing, you have to maintain the charge neutrality. So the electrons of this zinc are not being used by any other. It is not a reaction here, please see, it is not a reaction with some other substance. It is more of a decomposition process in which oxygen, a neutral molecule, is released from negative ion oxygen minus. So the extra electron of this, which are 2 minus, they are left behind, and they will definitely go back to some interstitial site. But in the entire process, you have lost out the material or element which was forming from negative ion O minus 2, है ना. तो एक्स्ट्रा क्या बच गया, मेटल का आयन. दैट मीन्स दिस ऑल्सो बिलोंग्स टू मेटल एक्सिस डिफेक्ट. दिस वॉज वन एक्सपेरिमेंट दैट आई टॉक्ड अबाउट जस्ट नाउ, the way in which you can imagine the formation of metal defect. But this is another way also when you heat zinc oxide. That's why when you heat zinc oxide substance, it becomes slowly, then the whole of the substance now becomes little bit yellowish, and that yellow is because of these again F centers here. Example, one is this, another is this. All I am saying is you ended up creating free electron, but without disturbing the overall charge of the crystal. People should not think that we have created new charge as negative charge. No, this is separated, but overall charge is still 0, because यहाँ पे आपने न्यूट्रल में से न्यूट्रल को निकाल दिया, बट चार्ज तो ओवरऑल चार्ज तो अभी भी 0 है ना. जिंक 2 प्लस एंड 2 इलेक्ट्रॉन, बट ऑल आई एम सेइंग इज दिस जिंक 2 प्लस विल नॉट accept this electron, but this electron will be free. This will still remain in the ionic form. So this will definitely occupy the central position from where the O2 minus is missing, right? And that is what it will lead to the F center. So this is also one kind of example. Okay, and this brings actually yellow color. One may ask the question, why do we have to do this? Well, I am saying that in the process of formation in some method of zinc oxide, you may be heating that, some heating may be required, so this may happen automatically, or in some other process a little bit of temperature variation can also bring about these changes. Okay, so these kind of changes can be seen. Okay, the another deficiency that I want to discuss under the category of non-stoichiometry. By the way, why non-stoichiometry? What is the non-stoichiometry here in these two type of metal axis and metal deficiency defect? Where is the non-stoichiometry? In this case, whatever we have discussed, do you see that something in this case metal atom was added, right, and no chlorine extra is added, so this definitely brings certain non-stoichiometry in overall NaCl crystal. Similarly, from here oxygen is lost out and zinc now remains in excess, so this also brings a little bit of non-stoichiometry. Okay, now another way of introducing non-stoichiometry and the way in which we find is called metal deficiency defect. See, when I was talking also about this FeO, in the preparation of FeO by any method, okay, generally we expect that these two guys should be 1:1 ratio, but the kind of method involved, and also I said that temperature variations which are involved in the process, they simply sometime lead to various kind of changes. Okay, I'm not saying all the time oxygen will be lost, but something else also can happen. Okay, and this makes us getting FeO not always in this 1:1 proportion. That means this is ideal situation which we expect, but what we get in some cases, as I said, it could be Fe 0.95. This overall thing is balanced, the charge is balanced. We are not talking about the variation in the valency, please don't get confused with that. This may think that okay, the valency is different here, this oxygen has different valency and Fe different valency. It's not that, the valency is not affected, you are still talking about Fe2 plus and O2 minus, but thing is that the ratio in which they are combining to form is this, something like this. It could be even Fe 0.930. okay, there are variety of these kind of ratios which are created, so this will definitely bring about a deficiency of metal in the preparation. So some of the Fe2 are definitely missing, that's what is causing this kind of resultant. This happens because you know that Fe can exist with two different kind of valencies, Fe2 plus also and Fe3 plus also. So what happens is, in the same of this crystal of FeO, basically you may have some crystal of FeO, you have large number of Fe2 plus but few of them as Fe3 plus also. That means you were expecting all the oxygen 2 minus charges to be balanced by 2 plus charges of Fe, but if you have Fe3 plus charges, then this for one Fe you are providing 1 plus extra charge, plus charge, right? So that means this extra charge of this Fe3 plus which are present in this along with the Fe2 plus, okay, only in minor amount, only very small amount, but that small amount is sufficient enough to provide the positive charge to balance the negative charge, excess negative charge which is caused due to this kind of imperfection. ठीक है, ये चीज़ क्लियर हो गई आपको? मतलब हमेशा आपको ध्यान रखना है, ये दोनों जो डिस्कशन हमने किए हैं, बच्चे ऐसे कंफ्यूज होते हैं, सोचते हैं कि इसमें एक्स्ट्रा चार्ज कहीं पे ऐड हो रहा है, कहीं पे निकल रहा है. नहीं, ऐसा नहीं है. हमने पूरी मैकेनिज्म आपको यहाँ पे बताई है. देखो, इसमें कुछ भी एक्स्ट्रा चार्ज नहीं आ रहा है ना, और इसमें कुछ भी एक्स्ट्रा चार्ज बच नहीं रहा है नेगेटिव की फॉर्म में, बिकॉज यहाँ पे जितने ये मिसिंग होते हैं उसके इक्विवेलेंट टर्म में जितना एक्सेस चार्ज इसको चाहिए होता है वो इसके द्वारा प्रोवाइड होता है. ठीक है, और मैंने जैसे बताया कि ये जो दो स्पीसीज जो हैं आयरन के सॉल्ट्स के अंदर एग्जिस्ट करती हैं जनरली. ओके, ठीक है, तो इतना क्लियर हो गया. सो दिस टू डिस्कशन वेर यू हैव मेटल एक्सेस एंड मेटल डेफिशिएंसी डिफेक्ट, दे बिलोंग टू नॉन स्टोइकियोमेट्रिक डिफेक्ट. ठीक है, एंड मोस्ट ऑफ दिस नॉन स्टोइकियोमेट्रिक डिफेक्ट दे ब्रिंग अबाउट द फॉर्मेशन ऑफ एफ सेंटर एंड हेंस द पर्टिकुलर कलर. ठीक है, देयर इज अनदर डिफेक्ट विच आई वांट टू क्विकली कवर, इज कॉल्ड impurity defect. There are two examples which are given in the book, this and this, but the story remains the same. Let's take this one. Suppose if you take NaCl, okay, आपने solution बनाया NaCl का, saturated solution, and in this solution suppose you add a little bit of very small amount SrCl2. Again one may ask the question, why are you adding? Well, I am just adding simply because let's see what happens, that's all in this case. So SR has a different valency 2 plus and Na has 1 plus valency. ठीक है ना, only as an impurity, only very small amount in the form of impurity. अच्छा, तो ऐसी बहुत छोटी सी अमाउंट जो इम्प्योरिटी के फॉर्म में रहती है उसकी हम जब बात करते हैं, now if that is also there, somewhere if the size of the two allow sodium and let's say chloride, it's not a random combination. Certain salt only can be considered as an impurity to be embedded in the crystal, right? So once in a while along the lattice side you may see that instead of sodium ion there are SRs 2 plus. But then do you also agree that this itself brings a charge imbalance, because SR has 2 plus charge and sodium has plus 1 charge, naturally it will bring, है ना? तो इस बट वो चार्ज को फिर बैलेंस कैसे करते हैं? मैंने जैसे बताया तो सॉलिड तो पूरा न्यूट्रल लेना चाहिए, वो सॉलिड न्यूट्रल तभी रहेगा कि अब आप 2 सोडियम के बदले एक SR को एडजस्ट करो, है ना? तो ये पूरे क्रिस्टल में आप जहाँ जहाँ पे भी SR पाएंगे तो आप देखेंगे कि उसने इस SR ने एक साइड तो जो था वो वहाँ पे सोडियम होना चाहिए था, दिस इज द साइट, ओरिजिनल साइट ऑफ Na+, एक वो ऑक्यूपाई तो किया है, उसके साथ में एक और साइट जो है जहाँ पे सोडियम मिसिंग होगा वो भी क्रिएट होगा, सोडियम मिसिंग। तो यहाँ पे ये मैं बताना चाह रहा हूँ कि आप देखो चार्ज डिफरेंस है यहाँ पे, और इस चार्ज डिफरेंस के कारण दो अलग अलग टाइप के अगर आप मेटल आयन लेते हैं किसी क्रिस्टल ग्रोथ में, अनाइन तो कॉमन है तो उसका तो कोई इश्यू नहीं है, तो ये जो चीज़ है वो बहुत छोटे अमाउंट है, मैं नंबर 1, but you will definitely get it embedded somewhere because the sizes allow, number 1, but to maintain the charge balance for every strontium the 2 sodium ions are missing. This leads a kind of a certain kind of vacancy here. Okay, so the charge, in order to maintain the charge neutrality, this kind of imperfection happens. So this is called impurity defect. In the previous case when I was giving you the example of iron 2 plus and iron 3 plus, यहाँ पे भी कुछ ऐसी स्टोरी होती है चार्ज बैलेंस करने के लिए, लेकिन ये दोनों सेम मेटल एलिमेंट है। देखो आप आयरन है, इसमें सेम मेटल एलिमेंट नहीं है, अलग अलग टाइप के हैं, यहाँ पे भी वही स्टोरी हो रही है जो मैंने ऊपर बताई है, ठीक है। लेकिन आपको ये अप्रिशिएट करना है कि यहाँ पे हम एक फॉरेन एलिमेंट की बात कर रहे हैं, दूसरे टाइप के एलिमेंट की, ठीक है।